Hello and welcome everybody to n-Simplex Pachinko. I am Obi-Wan Pez, your host for the evening. What am I forgetting? Sorry, I yet again started this without actually being able to hear myself, so this is a little distracting. Alright, so for tonight we're going to talk a little bit about the research that I was doing concerning the n-Simplex, and yes, that is where the name for this channel came from. Unfortunately, there's kind of a good news, bad news thing going on. Alright, so I watched a video this week which cleared up a whole lot of stuff and made me realize that I'd been going about my research on this thing kind of the wrong way, and that was alright. And it gave me a major breakthrough in order to figure out what the pattern is going to be for dealing with stuff inside the n-Simplex. So, I had mentioned that basically the idea was that when you're looking at, I'm going to do this like once every couple of months, it's fine. When you're looking at n equals 1, basically this is a really boring sort of thing. You start with a node which has one way to get to it. You're there. And then we're going to move down. And there is precisely one way to get there. And precisely one way to get there. And I think you're seeing a pattern here. Precisely one way to get here. So this is just going to continue down. In the 2-Simplex, also known as a triangle, what we have is we start with a 1. Our nodes then split to two possible locations, which are, again, both 1s. And then from here, this is where it gets a little interesting. There's still one way to get to either of the edges, but in the middle we have this 2 now, because there are 2 ways to get to the center section. Yes, hey Super Red. Yes, simplices, yet again. And then we can also continue this on. This is going to be 1. This is going to be 3. This is going to be 3. And this is going to be 1. And like I've said before many times, this is going to keep continuing. Interestingly enough, right, we can see the 1-Simplex inside of the 2-Simplex as both of the edges of this thing. The 2-Simplex is similarly repeated on the 3-Simplex when n is equal to 3. This is going to be awful. I'm adding perspective. It's fine. So we get the 1, 1, 1, 1, 2, 1, 1, 3, 3, 1 pattern that we do above, but also this is going to occur on this face as well. And it also occurs on this back face as well back here. And yeah, this is going to be really messy. Ooh. So we get another 2 back there. I got you. So I was having problems trying to figure out how to do this in Python, just because I was trying to think, like, how am I going to have a, 4-dimensional, 5-dimensional, etc. Like array. And so my spouse was saying, well, you might be able to like nest arrays inside of arrays. That's a thing. And I was just like, yeah, sounds like something I don't necessarily want to do, but if that's the only way that's going to work, sure. Anyway, this is when we start running into some problems, though, right? When we start looking at like n equals 4, how exactly are you supposed to write a 4 simplex? Um, it gets to be a little bit of a problem, but basically, you start with a 1, which is itself a like the basic 1 simplex, and then you end up with a tetrahedron, which is the 3 simplex, and in 4 space, you have all the possible options to get here from the first one. So you can get to any of these 4 by taking these paths. And then we're going to have a larger tetrahedron with sides 3. That was a bad idea. So this sits like this. Now the thing is that you have to be careful about how exactly you put in these individual points, but it essentially ends up with 1s in the corners again, just like we do for all the rest of the simplices, but then the middle squares are different because now you're trying to see like how many of the above ones are actually going to connect down onto this layer. So we end up with a bit of a problem. In the 4 simplex, you're going to find this faster than I will. In the 4 simplex, right, what are the terms we get? Here we are. Star args. Alrighty. That would help. Let's see. In 4D space. This was going to be a field of 2s, I believe. Right, because each one of these is going to go to is going to get assigned to a specific corner. So then there's only 2 possible ways to get to any of these, because again, we're doing 2 moves essentially. So how to get down to this row, there's only 1 possible way to get to each of these, but then when we go down to the next layer, either you can go out to one of these here, followed by that one there, or you could have gone to this corner, which gets you to that corner, or to there. Right, okay. So it's going to be multiple 2s on all the faces. all the middle faces. Sorry, middle nodes of all the faces. Yeah, I mean, I have the actual formula here. I'm just being lazy about it. Right, so then we're just gonna go like this. Who's old Horatio? Is that Sea of Thieves or Final Fantasy 14? Right, so then like n equals 5 is where it gets insane, because for each layer, basically this stuff is one face of the 5-simplex. And then you've got to do that for all the rest of the faces of the 5-simplex. So there are going to be five faces, all of which look identical to this thing. And they're just, you can't even visualize it. I mean, it's just insane. So what? Anyway, what happened this week was that I was watching a noise. Right, so I was watching a video that had to do with this was atmospheric physics, specifically particle physics. In the upper atmosphere. So the person in question runs a channel called Radius Cubed. On YouTube. And he is a grad student in Colorado, and was talking about how the Pascal triangle can be overlaid onto a what's called a Galton board. Oh boy. So the Galton board is this really cool device that has like a little funnel slash pouch at the bottom of it, which collects all of these into, yes, there you go, which collects all of these ball bearings, and then you flip the whole thing over and it starts dumping the ball bearings out the top. And it has a pachinko board in it. In 2D. And so it's, approximately the size of a ball bearing, a little bit deeper. And then they all bounce down and filter down to fill in all of the little spaces that they have at the bottom. Right. And this is like that game show, or the game on The Price is Right, called Plinko, which does the same thing. It's just that at the bottom, each of the bins are filled with like price values. So you try to hit the one that's right in the middle, because that's like $5,000 or something, and then there's zeros right next to it, and then there's 1,000s outside, and then 500s, and it keeps going out. So you could pretty much go for almost a guaranteed thing and go way out to the edges, but then you get very little money. Or you throw all your things in the middle and just hope that the math plays out. And it's going to hit either the direct center, or not the one next to it, but the one after that. And again, if you work out some of the probabilities, you can figure it out. But anyway, so the Galton board was this thing that was invented in like the 1800s by this guy Galton, who made this physical object to describe what was happening with this binomial distribution. So this guy on Radius Cubed went and um, was like, okay, just thought experiment here. As it turns out, right, when protons come in as cosmic particles around the Earth, right, they end up striking the atmosphere and causing muons to be created through the, you know, collision of energetic particles. So and these muons, like neutrinos, can be detected, uh, or we have detectors for them on the other side of the planet. Some people are like, wait, what? Um, so the way it works is that the muons actually basically don't interact with anything, specifically neutrinos, but a lot of other stuff too. Just don't interact with normal matter. So, or almost ever. So that they can fly through basically the entire Earth without striking anything. And then on the opposite side, there's like these really huge, deep swimming pools with heavy water in them. And as they go through, they actually do interact with some of the particles. They don't interact with most normal matter, but you know the heavy water has the ability to at least be detected when it's struck by one of these muons. It makes a very clear signature. If we do it on the front side of the planet, we end up getting a whole lot of other interference that's striking it. So we're like, okay, well, we don't want all of these other false, what turns out to be false positives, right? These other particles that are coming in that we don't care about. We don't care about, you know, some of the other stuff that's coming in. So we put these detectors on the far side of the planet and, you know, wait until nighttime for that part of the planet, and then you can see the muons striking the water. Well, when the muons hit the upper atmosphere, they tend to scatter in sort of a pattern that looks maybe like this-ish. Now there are hundreds of thousands, millions of them at any given time that are just passing through all of us, our bodies, the earth, everything. And most of them, again, don't interact, but when the muons get created from the particle collisions... Wait, I just contradicted myself. Okay, cool. As they start losing their energy, we start seeing more and more collisions, and so you can get kind of this interesting pattern to it. So Radius Cubed was saying, okay, what about, like, can we model this? What is this in mathematics? And I went, this sounds familiar. And you look at the number of pattern, or the number of different paths that a muon can take before it reaches the same place. And lo and behold, if you look at it in 2D, it's a Pascal triangle. And I went, oh. And then he said, okay, so if we start looking at this in terms of like, essentially, but it gets even better. It turns out that the 3-simplex pachinko that I've been looking at, and that like I've created that, or I had the engineering department at my school create this physical object. I still have not sent him an email to say like, hey, how's it going? um, so anyway, the physical object that I helped create, design, and the engineering department has now created for me, I hope, um, only has a choice of 3 directions. And this guy said, so what happens if we just pick, like, some number of bins that any particle that's striking it, if you're looking at it top down. So if it strikes this particular yep. There are multiple ways in which you might see this coming. So this object, this muon is coming straight down on this particle. If we choose a random direction and we say like this is going to be like this many, then this is one of 16 possible directions. So if we choose one of the 16 directions at random, then go a set distance before it comes down a layer and strikes a new particle, right? This isn't how reality works, but we're idealizing for mathematics. What happens, right? So it's going to strike this object. It's going to go in a random direction. It's going to go downward, downward, and then it's going to strike a new particle on the next layer down. So then, when it reaches that one, it's going to strike a random direction for the set distance, and it's going to go down again, another layer. The way that he did this, he ended up creating basically this whole thing. But again, each step that he went down, it was a set distance in the vertical direction. So instead of being an actual thing like this, right? He said that each particle is going to pick a random direction from top down. This ends up being a 16-simplex. So I picked one of 16 directions on every chance that we move down. And it also makes it, if you look at this, it's not just a 16-simplex. It also simplifies. Because if I choose a random direction at every individual point and then walk a certain distance, you probably know where this is headed to. I have in fact said both words. Right? So we go like a normalized vector distance for all these individual things, and we again choose random directions. And if all of these are vector normalized for distance 1, and all of our directions are absolutely randomized, then this ends up being a 16-simplex random walk. So this is actually a 2-dimensional random walk. Okay. So random walk is just basically like you're going to go a set distance at each interval. You're going to choose a random direction and then move forward that set distance. Again, what he did was that he had those project downward every time that a direction was chosen. He would basically move it over to that new location and also down. So the vector was always a 1x1 in some direction. and he was wondering why there was a factor of the square root of 2 in it. And I went, oh, buddy, you're, you're going one sideways and one down every single time, and you wonder why there's a factor of root 2 in there. That's exactly what happened. It's factored out from every single one of these terms. So, yeah, so the random walk basically just starts moving like Brownian motion. Um, it just moves in a random direction every time you move, and then it progresses, processes, does all sorts of stuff. If it's biased, either toward a particular point or direction or away from the center or stuff like that, then you'll have different probabilities and different amounts of stuff. What you'll see here is that if it's a true random walk, you could have 6, 10, 20 different simulations all at once, and they all start overlapping each other quite a lot. And they tend to be focused around the center-ish, because, just like the Pascal's triangle, we tend toward the middle in terms of not on any one trial, but after many, many, many trials, they will eventually tend toward the center, right? There are more options, more opportunities to reach the stuff in the middle than there are reaching the stuff on the outside. And then again, once you look at this in terms of do like 1,000 trials or 10,000 trials, when you're moving all of them down every step that you take, in addition to whatever direction you're moving them in, then this ends up creating these are not random. That was not, no. Ends up creating something that looks roughly like this. And it is like almost exactly this like paraboloid shape. So it's this super interesting, yeah, it's a super interesting paraboloid shape, which in theory, the outer bound is actually a cone. Because again, if you happen to always pick going outward at an extremely unlikely probability, then it will be that, it will be conical. But the outer bound in reality typically ends up being some sort of paraboloid like this. So, as soon as I saw this, I went, oh no. Here's your connection. The 16-simplex, or in fact, what he had suggested was, well, you don't have to pick a direction like, in a finite sense, in a discrete sense. You could do this in a completely 100% continuous sense, that there is going to be some angle theta, which is going to be your new direction. And every time you can just pick a new random angle from 0 to 360 degrees, from 0 to 2 pi radians, pick a random direction, move down one layer, pick a random direction, move down one layer. And again, just keep repeating that pattern. And I as soon as I saw that, I was like, oh, there's my research. That's it. That's all of it. Which, I mean, it's awesome because I was like, here's here's an inspiration that I could do something with it. And then as soon as I saw it, I was like, oh no, it just simplifies to the random walk. And right, there's in theory years of sitting there thinking to myself, what is this thing? Just summed up in like 2 minutes, which by the way is very well defined. Has been done thousands of times by all sorts of people. I'm like, oh no. So the idea is very well explored. However, this is, in theory, a new formulation for it, in that I didn't look at this in terms of um, I didn't look at this in terms of like trying to find a Galton space solution. So I'm going to call it Galton space at this point, where you are doing, again, a random walk with n choices, n bins that are now surrounding your strike point right here. So in a finite version, in a discrete version, you've got something that looks like this. And you are going to go in one of these set directions. This essentially makes it look like, if we just do the 8, if we just do 8 bins, right? As soon as it strikes this, it's going to go into one of these here, and this ends up being an n-Simplex. So now I could calculate what the individual probabilities are based on the n-Simplex in this particular arrangement. It only has to be a 3D space. In fact, it can be a 2D space that I'm drawing this in. And then like on the next layer down, it's doing another strike on that middle point. And then which direction it goes in, which bin it goes in, is going to be random. So again, now we're at another node for the n-Simplex. And I was just like, okay, well, that's that. In theory, this does mean that, like, I can't draw it, but I could, in theory, think of this as like, okay, this is going to be the point where we hit, and then it's going to bounce into one of these bins, and then on the next layer down, directly underneath where it falls out, is going to be another point for it to strike. And we could determine, in theory, how many different arrangements can you get into each of these bins, depending on what layer it's on. And again, we've already done the basic math for this in order to figure out where we are. Right, this is going to be the particular location that we're at is going to have a value equal to n factorial over pi as I goes from 1 to m minus 1 of k sub I factorial times n minus the sum as I goes from 1 to m minus 1 of k sub I factorial. Oops, nope. Take that back. N minus k sub I factorial. So what we've got is a product of all of the individual bins that this could have fallen into. Yeah. Yep. So I did finally find my notes that were like 4 years old. They are a mess. I mean, of course, but yeah, I even wrote right here 3D model because I was just so excited. I was like, dude, I can model this thing. Um, this was back when I was thinking only in terms of 3 dimensions. So, you know, literally I could create a model for it or like a physical object. That's what I wanted more than anything else. So I asked our dean and he was like, oh, absolutely, we're doing this. Right, and if you wanted to write it in n-choose notation, that'd be n-choose k1, k2, all the way out to k sub I. So how many layers down are we? How many choices have been made? And on the bottom, how many of each direction has been chosen? So if we label these in angular order, 1, 2, 3, 4, 5, 6, 7, and 8. Then how many times have we chosen a 1? How many times have we chosen a 2, etc. all the way around the all the way around this. Let me do it properly. A, B, C, D, E, F, G, H. So we could label these as, you know, K1 is A, K2 is B, all the way out to K sub I in this case would be H. So how many of each of those have we chosen and what layer are we on? Then we could figure out how many different paths there are to get to that particular location. Yeah. Yeah, so I found this on my own on a car trip and I was just like, oh man, because I was just doing the regular n choose k formula and I'm like, but then we're adding another dimension. Like, how does that work? And it just turns out that it's just a factorial of all the individual choices you've made. I'm like, come on, man. So actually, yeah, I didn't. Oh, you know what? I didn't even need this factor. N factorial over the product as I goes from 1 to m of just k sub I factorial. Right, going all the way out to your last one. Well, I guess that's technically k sub m, but eh. Yeah, I was floored by this just because, and being away from the internet for a little while, I was like, I've invented something, and oh, 20-something-year-old me. Um, no, actually, it was 34. But yeah, I was just like, I went and I looked it up on my phone. I'm like, oh, like, this has been known about for hundreds of years. I should have known better. uh, or like 100, 150, something like that. It was either way. It was. I did not discover this. So I got my hopes up again on this one. Yeah, no, I mean definitely like, and this is the thing is that the connection, the way that I've gone about it, might be something new. I don't know, but could be. Or at least the connection might not be known about between the, n-Simplex random walk or the n-Simplex like triangle, the n-Simplex Pascal scheme, right? Might be completely new when you're looking at it in 7, 8, 9 dimensions, and then looking at this from this perspective and saying that all we're doing is we're making like 2D choices in a random walk. And so, yes, this continuous one ends up being essentially an infinite simplex. But, like, yeah, there. So that's the other thing is that technically with infinity, right, you're never actually going to choose literally the same path. It's not possible. So if you end up having something be literal infinity in terms of what choices you can make, you're never going to reach the exact same part. So you have to split them up into finite bins. You have to, because otherwise it just doesn't work. But that's the other thing is that this now becomes a, muon scattering random walk with infinite choice. So now you can actually show like what's going to happen through a million, you know, a million trials of this, right? Pick a random angle, truly random angle, and then do a million, uh, or like 1,000 steps or 100 steps or something like that, and then do a million trials of that. And then at the bottom, this is the key. At the bottom, you have to choose a finite bin size. So you could have it be a infinitely continuous thing up top, and then down at the bottom it turns into discrete. And then you look at the statistical analysis that goes on there. But anyway, I'm sure this has been done, but I've never seen it. So I would be really interested in finding out. Um, I'd be really interested in finding out how to make that. I don't know. I guess try to see if the connection is. I'm having trouble finding the words. Try and see if that connection is something that is new. That we can make an n-Simplex. That we can make a continuous function for the angle, or continuous whatever. Continuous random. Oy. Pick random angles, go down, however many steps, and then choose a bin size at the bottom to show the statistical analysis that exists. It's gonna be weird. That's alright. I'm okay with it. We'll just stick and homework help on the end there. Maybe somebody will be enticed. Alright, so so yeah, in about 24 hours, I contacted the guy who's I was able to find him very easily because he gave his name and where he worked in his video. Bad internet security. Um, but no, seriously, dude, awesome job. Um, no, he did it. He did it on purpose but he has a small enough channel, it doesn't really matter. I have a small enough channel, it's not going to call attention to it. What? Sorry, Super Brain, I think I missed something. Oh, okay. So yeah, he was able to get his anyway, I contacted him and was like, "Hey, do you want to like pull some notes on this or whatever?" And he was like, "I'm really busy with a lot of other stuff. Like, you can go ahead and take it if you want." And I'm like, "Oh, that's really nice. Thank you." Um, gotcha. So he's like, "Oh yeah, you can take that if you want. That's, you know." And I was like, "Yeah, I'll let you know if I get anywhere with it." And within 24 hours, I figured out, "Oh no, it's the random walk. Oh no, it's very well documented." And so I sent him back an email that was like, "Yeah, there's there might be some connections here, but it's not going to be anything, you know, anything brand new. This is what it's called in mathematics." Yeah, but I mean, it's still cool. There maybe, like I said, maybe there's a connection that wasn't thought of, and maybe I can get a paper out of it or something. But it's a little disappointing to be like, oh, this here's a brand new thing I'm working on, and then it's like, no, no. I was I was about this close to passing this off to a student as well, and being like, hey, do you want to do do you want to do like a research project on this? Because that would have been embarrassing if it was if they were like, hey, this research project lasted me a day. Yeah, it would be brand new to them, so it'd be kind of fun, but still. All right, if there is anyone else around who would like some information on, who knows, anything you're looking at for homework type stuff, I am willing to help out a bit and try to explain things better. Um, Typically, how we do it on this channel is that I have. We don't even have a queue because, well, quite frankly, we don't need one. um, Hang on one sec. All right. So anyway, um, yeah, we don't have a queuing system here because there aren't that many people who ask questions. Um, so in the future, we might end up needing a queuing system. I've been on uh, channels with Megalomorph and um, Tayo Inoue, who have both, figured out this whole thing, have been streaming for much longer than I have, and have a much wider audience base. um, so maybe someday. but we'll see how it goes. Ooh. Yes, cool. I'm glad to see that I have ignited an interest. Yeah, it was an interesting that particular thing was a very interesting like diversion compared to all of the usual 4x4 with squares or 3x3 with larger numbers. Hmm. Should send that into the International Database of Sequences, whichever one. What's that called? Yeah, that one. Oh yeah, yes. Yeah, I've popped on there a few times actually to check the check some of the stuff with the n-Simplex because I was able to see like, okay, if we just go this way and like read all of the layers of our, Pascal triangle left to right, what do we get? And what about the three-dimensional one? What about the four-dimensional one? And yeah, they're all there. So then I also started looking at the different formulations and what happens if you start adding up um, different amounts of stuff. So I also told you about this one a while back. What happens if you are going to take your Pascal triangle, and you add up not the two items above it, but yeah, the summatory. That's what they call it. Yeah, the summatory Pascal triangles. So that like this one ends up being the sum of everything above it, and this one, well, that's just symmetric, but this one ends up being the sum of everything above it, like that. Yeah, I really liked pursuing this, and then I was like, oh, that's also there, man. Right, actually, right. You found the constant. So I went back and I found my Excel sheet at work that had all of the uh, different summatory triangles that went like, okay, what about just this triangle here? So if we only went up this far, it's 2 rows. Okay, what if we went back 3 rows? What if we went back 4 rows? And all of that. I started climbing it and then finding the ratios of the successive rows. And yeah, it was 3.414, etc. So it was 2 plus root 2. Exactly what you found. I mean, not surprising, but when I went back, I was like, oh yeah, right. Of course, it was that number. Got all the evidence for it. Yeah, and like I also did not have code at that point because I decided that this would be a great idea to just be like, hey, let's just wing it and throw it in an Excel spreadsheet. And it wasn't even that's the other thing. It wasn't even a database. It was a spreadsheet. It's just oh man, so bad. I tried actually moving everything over to a database, and I was like, I can't understand access, which is too bad. And then at work, I don't have access to Python, so I have to do any Python work at home, and any MATLAB work I have to do at school. I mean, MATLAB I can still do on Octave technically, and there's an online Octave, and I can download stuff. And I also have Scilab, so there's all that. But Anyway, yeah, Excel's definitely the place. Oh man. Yeah, so then the next step is, what about the summatory what about these summatory simplices? And that is going to completely destroy me if I attempt. But anyway, it wouldn't be too bad if I just focused and actually did it. But my problem is that I have so many other things going on right now, especially correcting papers. Yeah. uh, right. And you have to come up with a scheme in order to figure out how they're going to be added, especially since when you're looking at it from any particular dimension, which indices need to be included or not included. Yes, PyCharm. Yeah, I like it. And it ends up being like the hyperparallelogram, yes, but at the same time you could just say that it's going to be an inverted um, it's going to be an inverted simplex of the same kind, just bounded by zeros. So wherever your indices are 0, you just say, well, you can't go any further. Just start incrementing back. Goodness. I figured out one of what was it? Um, Matt Parker did a uh, like math challenge series or something like that when he was doing, early on in lockdown, and one of them happened to be aligned with the Pascal triangle, and I was like, I've got code for that. So I had it in about 5 minutes and then sent it, and it was one of those things where it was like, oh, you know, 5,000 people did it this way. And I'm like, yeah, I'm in there. Probably not that many, but goodness. And then recently I was like, you know what I could do? Restart my Collatz branching. So at one point I was like, yeah, so I actually, um, somewhere, I'm sure I told everybody this one, but I was working on a D&D, or sorry, not D&D, Fantasy Age campaign. That was the same, uh, it was the campaign that Will Wheaton did on Geek and Sundry. Um, 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 Titan's Grave. And so his Titan's Grave campaign came out as a separate book through Green Ronin, and I was like, oh man, this is awesome. So I started doing, like, I started making the campaign. I started DMing the campaign for this particular group of friends that I had, and we got to this one town, and they were like, let's figure out the puzzle. And I'm like, I don't have anything. I, I literally, I do not have any content in this town, but they don't know that, and I'm not going to tell them. So they wander around town, and I had a, yeah. They wander around town, and I have notes on, like, what is in the town, roughly speaking. And they go to a, you know, some shopkeeper and start talking about it. And, you know, what's in town? And he's like, oh, well, we've got the, you know, tomb of the wife of, like, one of the most, well, she herself is a founder of, like, the whatever world is being built here. You know, she's a founder of this nation, and also she married one of the other founders of the nation. So, like, the two of them worked on this together. The guy disappeared some hundreds of years ago, and then she lived in this town until she died. So she's got a tomb there. And they were like, let's check out the tomb. And I'm like, ugh. And they're like, okay, well, there's got to be, like, a thing here. We can, like, and I was like, there's a, you know, metal chain thing that's around, like, a little garden plot, basically, that has the stone, like, carved into the wall. They're like, I want to get up and read it. I'm like, okay, you can read it from the side. And he's like, no, I want to, like, get into the little roped off area. I'm like, so the captain of the guard comes over and is like, what the f are you doing? And the thing is that this town is super strict about rules. And if you break the rules during the nighttime, and it's not actually nighttime, it's like the time during which it's like the king of day and queen of night. So if the queen is on the throne, she just, like, basically has summary judgments of just, like, toss him into the dungeon, kill him, do whatever. And I'm like, ugh. You guys are getting awfully close to the time when the switchover is coming. So I don't think you want to mess around with this. So I was thinking, like, if nighttime comes, then this captain of the guard would be like, oh, look, you guys screwed up, and just grab them by the collars and toss them into jail. And then I was like, I can make a Colats dungeon. They get tossed into, like, a prison room that's numbered somewhere out here, and they have to find, like, you know, journal entries and things like that that are going to give them hints as far as what needs to happen. And one of them was fairly familiar with mathematics and puzzles, so I get the feeling that he would eventually catch on and be like, wait a second, I see what's happening here. But, you know, that's the weird thing about Colats, is that, like, you know, 3 is out here. There's some other smaller numbers that are, you know, way out in weird places. I think on this one I've got basically all the numbers 1 through 40 or something like that, but yeah, that's probably a lie. But oh man, that group was crazy. I I loved being their game master, but in some ways I'm kind of glad it's over. So because one of the guys was just like total murder hobo and was gonna get in some serious trouble eventually. So one of the things that I've been doing with this, which not much, um, is basically going out until I hit 1,000,000 in every direction, and then just like doing ... and saying forget it. Um, and fortunately, right, this is an exponential function, so it grows pretty quickly. But yeah, and that's also another interesting thing right here is the um, we hit 10, and then it just becomes the powers of 2 times 10. It's anyway, it's not like weird or anything. Of course, that's going to happen, but so anyone have anything that they want to? I mean, it's going to happen eventually, right? Maybe for now, 100,000's high enough. This is like my version of doodling or painting. Let's just work on some collats. Get a happy little tree going in here. Right, and then the other thing was that we've got branches every... this one, that one, that one. So the pattern here for the blues is that this is an this is an x mod 3 is equivalent to 2, I think it was. 53, yeah. So when you get x mod 3 is equivalent to 2, you have the possibility, not guaranteed, but you have the possibility of getting to this point. Sorry, no. Taking this number and going back to a different branch. So that's why when I'm coming down my list here, I'm going to say, okay, 160 is right, mod 3. 160 mod 3 is, that's 1. Hang on. No, it's when it's equal to 1. Okay. Oi. If x plus, no, minus 1, right? Over 3 is odd. Yeah, this was also something weird that happened. I got really deep into this. I think it was on my other sheet because I had like a huge amount of scratch marks. um, because I started doing one of these branches. I don't remember where it was exactly, but like it's a secondary or tertiary branch. And I came out here and I ended up with like an even number. And I looked at it and I went, wait, A, I've already got that number somewhere else. And B, if this is an even number, we're not doing the odd pattern, you know, the triple and add 1. We're going to be doing the even pattern, which is divide by 2. So of course we're not going to get from that even number to this odd number, which is the, oh, yeah, sorry, that was way off screen. Of course we're not going to get to this from an even number to a different even number by using the 3x plus 1 bit, because you don't do that. Right? When the number is odd, then you do the 3x plus 1. When the number is even, you divide it by 2. So I ended up, when working backwards, I ended up with a branch that would have used the 3n plus 1 on an even number. And so I said, well, clearly that's not going to work. Anyway. So if we add 1 to this, it's 2561. And then divide by 3 is going to be 8. 16 is, oops, oh, can't do that. 16 divided by 3 is 5, with 1 left over. Did I just screw that up? Probably. It's cool. Oh, no. Minus 1. Jeez. Alright, 59. 9 makes 3. So 853. Right, 24, 25, 50, 9. Plus 1. Yep. Yeah, and like I said, it's kind of like this is my mandala drawing. Where you've got people who do like all the little coloring and stuff like that. Yeah, this is me. So I'm doing Collat stuff. So this was also something that like, yeah, we've got people in when I was going to when I used to sing in a choir. Stupid COVID. When I used to sing in a choir, I would have this sheet tucked in my choir book, and like, you know, any couple of minutes or something like that, I'd just write down a couple of numbers. And some of my, you know, colleagues did knitting. Some of them did like read books or whatever. No, me, I'm just doing this. Or the adult coloring books. Not like that. Yeah, I was also a part of the bases that attempted to sing as low as possible. I ended up getting to a G sharp, I think. And yes, that one. The one that's below the bass clef. Man, it was... Oh, one of our guys could... Like, now, I could probably only reliably get to about a B. But, yeah. If you start, like, going onto a virtual piano or something like that, sing as low as you can. It's the next one down. It's crazy. But, yeah, we used to be essentially in a little competition between us. Oh, hey, Van Clarice. Hey, Brandon. Welcome in. Sorry, I thought you were Super Brain for a minute. I was like, what? Suddenly realized that's not the same person. So how you been? So 3,400. And -1 is 13. Yeah, singing was a lot of fun. Yeah, pretty much same. I should be correcting homework. Oh. Hopefully none of my students find this. So divide by 3, and you get 13 with a 1 left over is a 6. With a 1 left over is a 5. And that's 59. So then 3. Oh yeah, keep him busy. Like I said, you know, this is my version of a coloring book for adults. Nothing against the coloring books for adults, but let's say that's going to be a 1 there. Divide by 3 is going to be a 4 with a 1 left over. It's going to be 18 is 6, and then 39 again. Interesting. It's going to be a 13. We're getting an interesting pattern here too. We end up with this 4 and 13. We have 4 and a 13. Here's different. We have 53 at the end. It's not like it necessarily means anything, but it's just kind of an interesting idea. Any requests on things to explain better in mathematics? Maybe this was it. -1. No, because that's still going to get us an odd number. Okay. Alright, so this is going to be 105 divided by 3. It's going to be a 30. With 1 left over. This is a 5, so 15 is 5. Alright, so 423 divided by 3. 42 is a 14. And a 1. The weird ways I find to relax. Oh, this is the same. This is the same choir, by the way. Had a lady in it who's roughly about our age, maybe a little bit younger. You know, me and my spouse. And I was sick this particular week. Not like contagious, awful, but like head cold, and like my voice was just on the verge of getting better, But it was at that stage, I don't know if you all know this, right? When your voice is like an octave lower than it should be. So I'm down here talking like this. And I see her walking up, and she's wearing an N7 jacket from Mass Effect. So she walks up. I hold the door for her, and I nod and I go, Shepard. And like my voice is just bottomed out, and she's like, whoa. Oh my god, you've got a Rex voice. I was like, yep. Haven't been sick like that in several years. Oops, no, that's not right. Alright, so 6,784. Yeah, and as Superbrain said, right? Never thought about working backwards. So working backwards was like one of the first places that my brain went for some reason. I was like, how can I manipulate this? Because I know at the very least I can seed this with the powers of 2. So I just said, okay, I can go from 1 all the way up to, whatever I want. These are the powers of 2. This is like the spine of the entire chart. And then from here, we can make all sorts of secondary, tertiary, quaternary branches off of this and basically do whatever we want. 13,568. So, um, yeah, Brandon, I was telling Superbrain, I don't know if you were here for that, but uh, that I had made a dungeon out of this particular setup. Um, so it looks nice and neat right now, but this is what it looks like when it's expanded further. So, like, this is only a few different branches that go off in this direction here, and then, which way am I going? Yeah, then we can do all sorts of fun stuff, end up back off in these branches. So I was like, I'm gonna my players are gonna get themselves in a lot of trouble. I'm gonna throw them in a dungeon that's gonna be a bit like this, and they're gonna find like journal entries and things scratched in the wall, and eventually they would probably try to walk out by just going along the same path that like doubles the room number every time. So every room would be labeled with one of these numbers. I was like, oh, let's see how this works. And oh man, it would have been pretty awful. Oh man. Can we prove that the n-Simplex, each individual row is going to sum to k to the n? Okay, now that is going to be... You're saying that... Is this for the multi-sum, or is it just for the regular sum? Just for the regular... Okay. So a single row on the Pascal triangle, or a single face. No, we're cutting the other way. A single layer of the higher dimensional ones. 3D is a little bit easier because you're cutting that way. got this stuff, right? Uh-huh, yeah. I mean, it's got to be induction, right? Cooler yellow. Good evening. Yeah, no, um, this is a very basic tablet. This tablet is 10, 12 years old, something like that. Um, and it doesn't have a display on it. Yeah, my old dean, like who has since retired, probably 3 years ago now, give or take, raised my notes. Sorry. Oh, you mean just like grabbed here? All right, so for like n equals 2, we start with 1, and then we go with 1, 1, and then 1, 2, 1, 1, 3, 3, 1. So we know that at least for the ones that we see here, the sum of the entire row is going to be 1, 2, 4, and 8. So we only need technically one row for that to be true, but come on, right? Let's at least try to show that it's going to work. So then we assume that this is going to be 2 to the k for some row, right? The kth row. So then prove that 2 to the k plus 1 is what we're going to get on the k plus 1th row. Okay. So for this, we're going to end up getting 2 to the k I mean, I will happily play around with a cat, even though I cannot see the cat. It's cool. Watch this. That might be cruelty to animals. I don't know. Alright, so then if this thing sums up to 2 to the k, so we've got the sum of all n choose, technically it's just n choose k because we only need the 1 from I going from 1 to n. So I right, because we got choose 0, choose 1, choose 2, choose 3. 0, 1, 2, 3. Okay. We end up with this thing. Then k plus 1th row. We end up with the sum as I goes from 1 to n plus 1 of n plus 1 choose k sub I still. Okay, so this is going to be n choose 0 plus n choose 1 plus going out to n choose k sub, I don't know, n over 2, or like we could just do floor n over 2, it doesn't really matter. Plus dot 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 all the way out to n choose n. Or k sub n, well, whatever. It's the same thing, right? K sub n is n. This one is going to be n plus 1, choose 0. Plus n plus 1, choose 1. Plus going out to I mean, whatever. n plus 1 floor plus dot plus n plus 1 choose n plus 1. I mean, the company's good, so. Alright, so I have to get from here to there. This is adding a new term, and also... These are all the sum of n factorial over k factorial k sub I factorial times n minus k sub I factorial. And this one is going to be n plus 1 factorial over k sub I times n minus k sub I factorial. Both those are factorial. That's the sum. So all of our original terms up here are going to need an extra n plus 1. Because we're multiplying by, or we've got n factorial here, this is n plus 1 factorial. The only difference between them is n plus 1. And here we've got case of I. Here, technically, this I is different than that I, but whatever, it's fine. So the new term, case of I plus 1. Yeah. I mean, basically, you're taking the old one, you're multiplying everything by n plus 1. Then, we've got to multiply the denominator by n plus 1 as well, because otherwise that's going to be weird. All right, anyway. All right, now I'm just kind of curious. All right, doesn't look like any of my math people are on at the moment. Okay. 6. Whoa. Well, good evening, everybody. Happy to have everybody in. Hope you're having a good time. If you have any actual questions about, like, random stuff, feel free to interrupt, because, you know, Superbrain and I are kicking around this problem, but there's a good chance we're not getting anywhere with it. It's fine. We like kicking stuff around here occasionally. I will say most nights we do have... I know. I should be like the foremost expert on it. God, it's been such a long time. Not since Simplex stuff, but yeah, just like doing my last induction proof, like that's been a while. that's gross. Alright, cool. Whatever. My OpenStax book apparently just doesn't want to do anything right now, so it's fine. Whatever. Makes me sort of wish I had it physically with me. Alright. What the hell? Let's choose a random page on my differential equations book. Eh. We've got this open source text. I don't even know where it's from. Guy who runs the differential equations course just like found it somewhere. We've been using it for a few years now. It's a pretty good book, but like no idea where it came from. Alright, seriously. Let's go. Math. Calc 2. It's opening just fine now. Jerks. Alright, whatever. Alright, so my students mostly have done all sorts of stuff from differential equations in the last few days. We're talking about Calc 2 here. The next one is going to be sequences, infinite series, and all of the comparison and divergence tests for integrals. I'm not looking forward to this, but I'll be complaining about it next week, I'm sure. So I did want to give a shout out to Pavel Grinfeld, who has been working at Drexel. For, I don't know, many years, I guess. And he had a particular setup on his differential equations class. Now, he was actually doing partial differential equations class for, like, students who got into this crazy hard program to get into. And I think it's high school students or, like, low-level undergrad students who just are excelling in mathematics. So they, the program itself is called Lemma. I need to stop that. Okay. So the program is called Lemma, and it offers students the ability to see like really advanced mathematics and do some research at a younger age when they're not typically offered these things. So he was doing something for partial differential equations, and he looked at how ordinary differential equations could be reframed almost entirely by taking all the stuff that we consider probably like Unit 3, or at least the stuff that I considered Unit 3, which was second order, linear differential equations. And he was just like, we can do all of this instead of doing it right after first order. We can actually skip this and go from first order linear and Again, most of the time, this is the route you take. He said, no, let's do it this way. Let's go over to here, which is going to be systems of differential equations. And so we see something like right, xy as a vector prime is going to be equal to 1, -1, 1, 3, transform matrix of xy. So given this, how can we solve this particular system of equations? So what he did was he reframed this instead of, or he reframed the second order linear differential equations to say, instead of x and y being independent functions of each other, what if we use x is just x, but y is actually x prime? So this ends up being x prime is equal to 1, -1, 1, 3 as x prime. Then we could do this as a system of equations. This is going to be x prime is equal to, here is x minus x prime. And then down here, this is x prime prime is equal to 1x plus 3x prime. Something about that isn't quite right, but it's not a huge deal, I don't think. We'll see how it goes. So this one is 2x prime is equal to just x. This is x double prime minus 3x prime minus x is equal to 0. So I don't think this should come out with what I'm thinking of right now in my head. Well, let's see what the consequences of this are. So I'm probably doing this wrong, quite honestly. However, when we see this, right, x double prime minus 3x prime, if 2x prime is equal to x, okay, let's do this. Let's make this a minus 2x prime minus 1x prime. So x double prime minus 2x prime minus x prime minus x. So negative 2x prime is just equal to x. Sorry, negative 2x prime is going to be negative x. There we go. Minus x prime minus x. Says x double prime minus x prime minus 2x equals 0. All right, with this, we can find an equation that's going to work here. So Um, right. Sorry, I think I might be backwards here. But anyway, so Dr. Grinfeld said, let's solve systems of equations first, and then we'll get back to second order linear differential equations later. So the point is that here we have all of this stuff. This is let x equal some sort of function e to the rt. And whether or not we have a value in front is arbitrary. It's just going to sit there and it's going to get divided out from all the terms. If x equals e to the rt, then x prime is equal to r e to the rt. And x double prime is equal to x squared e to the rt. So if we replace all of these with this stuff, we end up with r squared e to the rt minus r e to the rt minus 2 e to the rt equals 0. Factor out e to the rt here. We're left with r squared minus r minus 2. This is what's called the characteristic. And here we just have to solve it like a regular quadratic. So this is going to be e to the rt, which technically we don't need at all, times r minus 2 times r plus 1. All right, since e to the rt can never be 0, each of those individually could be 0. We got r is 2, r is negative 1. Well, I shouldn't necessarily be getting that answer, so that's interesting. Oh man, what did I do? I should be getting values of 2 and 2 alone. So something's wrong here. Move both of these to the other side. We got positive this one, negative with these two, and then either x can be replaced by 2x prime, or we can split the middle term into two pieces. The negative 1x prime is going to be left over. Well, that wasn't supposed to happen. We ended up with an answer here. This should not be a single answer. It should be a... Well, yeah, it just means I screwed something up. probably this step here. Translating a system of equations into a second order differential equation. I think that's probably what I screwed up. Ah, crap. I still didn't send out something. One of my students asked me to send out earlier. Gonna have to get that as soon as I sign off. Alright, let's see. For which part? Yeah, I knew it was Pascal's triangle. Which part of that? Alright, let's see if I can find. You're saying the diagonals along the outside? Those being Fibonacci numbers are only what you get when you add the two previous numbers. So I think I was maybe hearing something else from you. I don't know. Bookmarks? Question mark? Okay. Interesting. It would have to be partial diagonals then, because you're only looking at differential equations book. Huh. Yeah. I can't get in here. So, have to go this way, I think. Look for previous enrollments. Yeah, okay. Sorry. The ones that are not... The ones that are offset each other, not the literal diagonals that go through everything, because those are infinitely long. You can't do that. Yeah. I got you now. Yep. So I got it. Textbook. Haha. Digital Commons at Trinity. Yeah, okay. So this is the uh, rather good, I must say. The hell? The hell? All right, don't do that one. Hang on. There's nothing here. Boo! I can't delete my own message. I thought I was a moderator. Come on, man. All right. Well, anyway. Why is there a semicolon in the middle of the? That doesn't make any sense. Okay. All right, that does it. Haha. All right, so bit.ly link. This is the differential equations book. If anybody's interested, this is off of the Trinity Digital Commons. And I actually like it. It is quite good, I think. Occasionally it is a little hard to understand, but it's not very much. I don't have a problem with it. Alright, so like systems of differential equations. 508. And how they relate to second order. Yeah, okay. Hmm. It's not helping. All right, well. Yeah, I don't know why I'm having such a hard time with this one. Because again, it should not be getting this. It should be a repeated root. So like if we do it by eigenvectors, right? I guess let's check to make sure it actually does it. All right, so xy, nope, not x, prime, equals 1, negative 1, 1, 3. All right, so eigenvectors are a minus I lambda, which is going to get you a determinant of that, which is 1, negative 1, 1 minus lambda, negative 1, 1, and 3. All right. All right, so 3 minus lambda. We want to take the determinant of this stuff. This is going to be the product of these two things is lambda squared minus 4 lambda plus 3. And this is minus a negative, so plus 1. Yep, that works fine. Equals 0. This one's working fine, because here we're going to get minus 4 theta plus 4. And when both of those lambda minus 2. Lambda equals 2 with multiplicity 2. So therefore, solution to this thing, x, y, is going to be equal to lambda 1, c1, well, not lambda 1, c1 e to the 2t plus lambda 1 t plus lambda 2 yeah, constant c1 and constant c2 kicking around outside. Right, there's ways to find the eigenvectors for this stuff. I'm not going to do it today just because pretty much reaching the end of my tether here. Not in the angry sense, just we're about done, I think. Sorry. So yeah, why aren't we getting that over here? That's the next question. It's a relationship that we can work out. Just going to get us exactly the same thing. So Hmm. At any rate, I will figure out what went wrong here. It's probably a simple, like, substitution error or something weird like that. At any rate, I hope everybody has a good week. I am going to come back on Friday for Game Stream. We have started in on the Forgotten City, probably. We've started in on the Forgotten City, which is yet another kind of time loopy sort of game. I have basically no idea what it's about, apart from the fact that there is a time loop and there is some sort of punishment that is enacted on all the people in the town whenever anybody commits a sin, whatever that is considered. So we have to watch out for that. I'm guessing that we have to find the person responsible, and I would also find it amusing if the person responsible is you. I know for a fact that I could probably trigger it, but not like when it's just triggered. I don't know who or where or when or how the effect is actually triggered just by itself. So this ought to be interesting. So we are going to head on over and see who we gonna see. All right, I think Jason Charles Miller is probably ending very soon. So okay, Megalomorph is not on. I don't think Tyone is on because that would be crazy. Yeah, he's. I think he's in the same time zone, so it's getting late for him. All right. Why don't we just look real quick here? See who else we got. Yeah, really. Not a whole lot of other people. Okay. So we'll go see Jason. Yep, no problem. And again, thanks for coming. Thanks for hanging around and asking a few questions. We'll see what we do. And next Wednesday, we'll be back for another math stream. Um, everybody out there, I am Obi-Wan Pez. This is n-Simplex.